London, 1917. Britain was running out of time. The First World War had turned into a mechanical struggle, and the machines meant to protect the nation were failing at the worst possible moment. German U-boats were sinking British ships faster than they could be replaced. Entire supply lines were collapsing because British engines were underpowered, unreliable, and dangerously inefficient. In a small workshop south of the city, surrounded by the smell of oil and steel, a young engineer named Ricardo studied a disassembled tank engine spread across a bench. He was in his mid-20s, already known for a mind that refused assumptions and demanded proof. After months of testing and calculations, he reached a conclusion that many senior engineers avoided. Britain's engines were not failing because they were badly built. They were failing because almost no one understood the chemistry inside the cylinder at the moment of combustion. Ricardo believed that the key to Britain's survival did not lie in thicker armour or heavier weapons. It lay inside the invisible chaos created by gasoline, when it met pressure, heat, and time. If he could decode that process, he could change the course of the war. He approached combustion with a scientific mindset rarely seen in early engine research. While most designers relied on trial and error, Ricardo built special test engines with transparent cylinder heads and measuring instruments capable of tracking flame motion. He treated each experiment like a physics investigation, noting the smallest change in pressure and temperature. One problem obsessed him more than any other: knock, the violent and uncontrolled detonation that destroyed pistons, wasted fuel, and limited the power output of every British engine. At that moment, the phenomenon was barely understood. Ricardo was determined to isolate its causes and remove them completely. His breakthrough came in the middle of the war. After countless tests, he developed a new combustion chamber design that burned fuel more evenly, reduced heat losses, and allowed significantly higher compression without destructive knock. The transformation was immediate. British tank engines became more efficient and far more reliable. Their range increased, their failure rate dropped, and for the first time Britain had an armoured vehicle that could move with confidence across the muddy battlefields of Europe. Without designing a new tank or developing a new fuel, Ricardo had solved one of the British Army's most urgent mechanical problems. Once the war ended, Ricardo realised that tanks were only the beginning. Aviation was the future, and aircraft engines faced limits far more dangerous than anything seen on the ground. Airframes were improving rapidly, but engines remained trapped behind the same barrier. High compression produced more power, but it also triggered knock. Every attempt to push an engine toward higher performance risked total failure. Ricardo refused to accept that limit. He built new laboratory engines, developed advanced measuring instruments, and began mapping the true behaviour of combustion under extreme conditions. His findings revealed patterns that no engineer had fully identified. He demonstrated how compression ratio, fuel quality, temperature, and charge motion interacted on a molecular scale. These discoveries formed the scientific foundation for high-octane fuel and high-performance engines. His work would later become essential for the Rolls-Royce Merlin and other power plants that shaped the air war of the 1940s. In the late 1910s, however, almost no one understood how far his research would reach. Ricardo was preparing the tools that would define the next generation of aviation science. Ricardo's goal was not glory or status. He cared about precision, data quality, and engines that behaved according to measurable laws. Yet his influence expanded far beyond what he ever promoted. His research guided fuel chemists, engine designers, and manufacturers who needed a scientific roadmap. Britain's industrial planning in the interwar period relied heavily on his findings. Engineers who once guessed now had equations. Designers who once hesitated now had confidence to push beyond familiar limits. In the years that followed, every major advance in British engine performance carried traces of his work on knock control, flame shaping, and combustion stability. The nation's ability to mobilise tanks, aircraft, and high-power machinery depended on engines that could run harder and longer than their predecessors. Ricardo made that possible by explaining the forces inside the cylinder with unprecedented clarity. The workshop experiments he had conducted during the First World War had become a cornerstone of modern internal combustion science. As Britain prepared for an uncertain future, a single question emerged. Had the engineering world truly understood just how much power Ricardo had unlocked inside the machines that would define the next global conflict? If you want more deep technical dives like this, consider liking and subscribing to support the channel. How far would Ricardo's research push the limits of combustion science in the years ahead? The interwar years were supposed to bring stability, yet for engineers the period became an intellectual battlefield. Nations rebuilt, industries modernized, and aviation transformed from a fragile experiment into a strategic priority. By the early 1920s, powers around the world understood that the next conflict would be shaped not just by armies, but by horsepower. Harry Ricardo saw this earlier than most. While governments debated budgets and policies, he focused on an invisible arena where the future would be decided: the behavior of fuel under compression. Aviation demanded engines that could climb higher, run hotter, and generate more power from less weight. But every attempt to increase performance exposed the same destructive limit. At high pressures, gasoline detonated uncontrollably. Knock was not only wasteful, it was catastrophic. Ricardo recognized that solving this issue required a precise understanding of fuel chemistry and flame propagation, something no institution in Britain had fully mastered. He set out to change that by turning his laboratory into the most advanced combustion research centre in the country. By 1923, Ricardo had developed a revolutionary testing machine known as the variable compression engine. It allowed researchers to adjust compression ratio in real time to observe the exact point at which fuel began to knock. For the first time, engineers could measure resistance to uncontrolled detonation with scientific accuracy. This machine became a benchmark tool for fuel analysis worldwide. Oil companies sent samples across the Atlantic to be tested. Manufacturers sought Ricardo's data to guide engine designs. The research quickly uncovered a critical insight. Different fuels had different knock thresholds, which meant octane rating could determine whether an engine survived or failed under stress. High-octane fuels allowed higher compression and, consequently, more power. This relationship became the foundation of modern fuel science, and Ricardo used it to accelerate Britain's aviation programs. He demonstrated which fuels produced the most stable combustion, how additives influenced detonation, and how compression ratio could be pushed safely beyond conservative limits. His results gave aircraft designers the confidence to increase power output without risking engine destruction. The work seemed academic on the surface, yet its strategic implications were enormous. A nation that mastered combustion could build faster fighters, longer range bombers, and engines that could operate at altitudes previously considered unreachable. Ricardo's research attracted the attention of the Air Ministry and key manufacturers. As the 1930s approached and global tension grew, the need for high-performance engines intensified. Rolls-Royce had begun developing new generations of aircraft power plants, including early versions of the Merlin. These engines demanded an unprecedented balance between power, weight, cooling, and reliability. Ricardo's research provided the scientific backbone for these challenges. His work identified how to manage heat flow in combustion chambers, how to improve turbulence for better fuel-air mixing, and how to prevent destructive pressure waves that limited compression. The influence of these findings appeared throughout British engine design. Engineers could now model combustion behaviour rather than guess at it. They understood how flame speed affected power delivery, how chamber shape influenced detonation, and how fuel quality could multiply output. This accumulation of knowledge appeared subtle, but it created a decisive advantage once war returned. Countries that lacked rigorous combustion science were forced to use lower compression ratios and conservative designs. Britain, guided by Ricardo's insights, pushed its engines toward levels of performance other nations struggled to match. Although he never worked as a military officer or an industrial executive, Ricardo shaped decisions at the highest level. Governments relied on his reports to plan fuel production strategies. Factories integrated his research into manufacturing processes. He trained a generation of engineers who carried his methods into the increasingly complex world of aviation. His work also guided the shift towards supercharging. As aircraft climbed higher, air became thinner and engines lost power. Superchargers solved part of this problem by compressing incoming air, but they also raised internal temperatures and increased knock risk. Ricardo mapped these interactions in detail and demonstrated how high-octane fuel, improved cooling, and optimized chamber geometry could allow engines to operate safely under heavy boost. These findings became central to British preparations for air combat. Without understanding knock at altitude, no amount of supercharging could deliver reliable power. Ricardo's research provided the confidence designers needed to build engines capable of both high boost pressures and long operational life. This meant faster climb rates, better interception capability, and greater tactical flexibility. By the late 1930s, Britain faced the growing threat of Nazi rearmament. Aircraft engines were no longer mechanical conveniences, they were national defences. Ricardo understood the responsibility placed on his research. He expanded his institute, increased testing capability, and refined the standards used to evaluate fuel behaviour. As the world moved toward another global conflict, he recognised that the future of British aviation depended not just on designing engines, but on supplying the right fuel for them. His influence extended into refinery planning, fuel policy, and additive development. Octane became a strategic asset, as important as steel or explosives. Countries that failed to produce high-grade fuel would face severe operational limitations. Ricardo's work provided Britain with the knowledge required to meet this challenge. Every data set he produced, every experiment he recorded, and every conclusion he published shaped decisions that would carry the Royal Air Force into the most critical battles of the coming war. As the shadow of conflict returned to Europe, one question became impossible to ignore. Had Britain fully understood how much its survival would depend on the silent science of combustion that Ricardo had spent decades decoding? What new challenges awaited Ricardo as the world moved toward the brink of war? By 1939, the world was preparing for a type of war, defined not by trenches but by altitude, acceleration, and mechanical endurance. Aircraft were becoming the decisive instruments of national power, and their engines determined who would control the sky. Britain knew it was entering this era at a disadvantage. The Luftwaffe had spent years modernising, while British industry had struggled through the economic depression. For engineers, the crucial question was not abstract, it was purely technical. Could Britain build engines that produced far more power from the same displacement without tearing themselves apart? The answer depended entirely on Ricardo's lifetime of combustion research. As tensions rose across Europe, the Air Ministry turned increasingly to the Ricardo Institute for guidance on how far British engines could be pushed, what fuels they would require, and how these machines would behave under wartime loads. Ricardo understood that the next conflict would expose any weakness in thermodynamics, metallurgy, or or fuel chemistry. He saw the danger earlier than most, which led him to accelerate every aspect of his research program. What had once been academic investigations suddenly became matters of national survival. The Rolls-Royce Merlin engine was approaching its critical development phase. Early versions lacked the power needed for modern fighters, especially when operating at high altitude. Designers needed higher boost pressures and higher compression, but both changes carried enormous risk. Increasing pressure inside the cylinders made knock more likely, and a single episode of detonation could destroy bearings, crack pistons, or rupture cylinder heads. Ricardo's data became the foundation of the Merlin's evolution. His charts on octane requirements under different compression ratios, his maps of flame speed under varying mixture conditions, and his detailed analysis of chamber geometry allowed the Merlin program to design for performance previously thought impossible. Ricardo demonstrated that carefully shaped combustion chambers and increased turbulence could control flame propagation even at high boost. He also showed how the use of high-octane fuel and chemical additives could delay detonation long enough for engines to reach unprecedented power levels. These insights gave the engineers confidence to raise compression, intensify supercharging, and push the Merlin far beyond its original specifications. What had been a good engine was now shaping into a great one, and Ricardo's fingerprints were visible on every major performance leap. At the same time, he tackled a problem that most nations underestimated: the behaviour of engines under rapid and repeated throttling. Air combat demanded sudden bursts of power, abrupt climbs, and fast transitions from cruising load to full boost. These changes created thermal and mechanical stresses that could easily overwhelm an engine. Ricardo developed tests that simulated combat conditions. He measured how fast combustion chambers heated under full load, how quickly pressure waves formed, and how fuel-air mixtures behaved during sudden transitions. His work demonstrated that engines did not fail simply from high stress, but from the rate at which stress was applied. With this insight, manufacturers redesigned cooling systems, improved airflow, and optimized fuel distribution. These changes kept engines stable during violent maneuvering, drastically reducing failure rates during early RAF training and combat operations. Ricardo had taken a chaotic, unpredictable environment and turned it into measurable, controllable engineering. Without this understanding, Britain would have entered the war with engines fragile under real combat conditions. Yet Ricardo's most critical contribution in the early war years involved fuel. As the Luftwaffe gained dominance across Europe, Britain faced a dangerous question. Could its aircraft match German speed and climb performance? The answer depended on octane. Standard European aviation fuel was rated far lower than the advanced blends developed in the United States. Ricardo's research proved that switching to higher octane fuel would instantly transform engine performance without changing hardware. When the British government adopted his recommendations, new fuel shipments began arriving from American refineries. The results were dramatic. Engines ran cooler, detonation resistance improved, and boost pressures increased safely. The RAF suddenly had fighters capable of climbing faster, turning harder, and delivering bursts of power unavailable months earlier. German pilots were stunned to find British aircraft outperforming earlier models, despite appearing outwardly identical. This advantage did not come from airframe design or raw horsepower. It came from Ricardo's understanding of combustion chemistry and his relentless pursuit of detonation-resistant fuel. It was one of the quietest but most decisive engineering achievements of the early war. Through these years, Ricardo continued refining the data that guided British engine policy. He produced detailed reports outlining safe boost levels, fuel requirements, and long-term engine durability. These reports shaped strategic decisions across the Air Ministry and the petroleum industry. He ensured that British and American fuel production stayed coordinated, that refineries understood octane targets, and that engine manufacturers had the scientific foundation to keep stretching performance boundaries. Each breakthrough pushed the Merlin and its successors to new limits. By 1940, some variants were producing nearly twice the power of early prototypes. None of this would have been possible without Ricardo's decades of work and the experimental framework he had built long before war arrived. He had given Britain the scientific tools to compete in a technological contest that favoured nations with deep understanding of combustion, and, as the Battle of Britain approached, that knowledge would become one of the most important advantages the RAF possessed. If you enjoy these deep dives into wartime engineering, a quick like and subscribe helps support more work like this. How would Ricardo's research shape the engines that carried Britain through its most critical air battles? By the time the Battle of Britain erupted in the summer of 1940, the stakes of Ricardo's work were no longer theoretical. Every British fighter that climbed into the sky relied on principles he had mapped years earlier. The Spitfire and Hurricane were icons of aerodynamics, but their true strength came from engines pushed to their limits through Ricardo's understanding of combustion stability, chamber geometry, and octane behaviour. The RAF needed rapid climbs, sustained power during tight turns, and engines that could tolerate violent combat manoeuvres without detonating. Ricardo had helped create these capabilities long before the first dogfight. His research on turbulence generation inside the cylinder allowed the Merlin to produce a cleaner, faster burn at higher boost pressures. His analysis of knock thresholds guided each major fuel upgrade. His influence could be seen in the engine's ability to use high-octane fuel safely, an advantage that allowed British fighters to push boost limits beyond anything the Luftwaffe anticipated. When the air battles intensified, this performance difference became critical. Pilots could climb faster to intercept incoming formations, sustain high power during turning engagements, and avoid engine failures during emergency manoeuvres. These advantages did not come from chance. They came from a scientific understanding of combustion that Ricardo had spent decades refining. As the war expanded, the demands on British engines became even more severe. The need for higher altitude capability grew as bombers needed to climb above enemy flak and interception paths. At high altitude, engines faced thin air, lower temperatures, and unstable mixtures. Superchargers compensated for pressure loss, but they also raised internal temperatures and increased knock risk. Ricardo provided the experimental framework to determine safe levels of boost at different altitudes, identifying how mixture strength, temperature changes, and fuel quality interacted under atmospheric variations. His work demonstrated that engines needed not just mechanical reinforcement, but precise mixture control and optimized ignition timing to avoid destructive pressure waves. Manufacturers used his findings to refine carburetors, improve intercooling, and stabilize fuel distribution across cylinders. These adjustments allowed the Merlin to maintain power at altitudes where earlier engines would have suffered catastrophic detonation. The improvements appeared subtle in technical documents, but were enormous in operational terms. Aircraft could now sustain high power in the thin, freezing air of the upper atmosphere, enabling bombing raids, long-range flights, and high-altitude interceptions that would have been impossible without rigorous combustion data. Ricardo's influence went beyond the Merlin. As the war progressed, Britain needed engines for bombers, naval vessels, armoured vehicles, and transport aircraft. Each engine faced unique demands, yet all shared one underlying limitation: combustion stability under stress. Ricardo provided the scientific basis for solving these challenges. He analysed heavy fuel behaviour in large displacement engines, guided compression decisions for engines operating under prolonged load, and advised the military on how to avoid premature ignition in high-temperature environments. Tank engines, often pushed to extreme loads in desert conditions, benefited from Ricardo's research on cooling flow, mixture distribution, and detonation control. Naval vessels adopted combustion principles drawn from his early studies, using more efficient chamber designs and improved fuel standards. Even the refinement of leaded gasoline, which became essential for wartime aviation, was shaped by research directions he had initiated. Ricardo's role was not confined to a single engine program. He had become the intellectual backbone of British combustion science, influencing decisions from fuel policy to frontline engineering. One of Ricardo's most significant, yet least publicised contributions involved the transition from naturally aspirated engines to high-boost, high-pressure power plants. Early in the war, most countries underestimated how far supercharging could push engine performance before knock became destructive. Ricardo's data proved that the limit was far higher than expected, provided fuel quality and chamber design were optimized. He showed manufacturers how to shape combustion chambers to encourage controlled turbulence, how to use squish zones to regulate flame spread, and how to design piston crowns that guided combustion without creating hotspots. These findings allowed engines to operate at extreme pressures for short bursts, giving pilots the ability to escape, chase, or climb when survival depended on raw power. This capability played a decisive role in numerous combat scenarios. Aircraft that once lagged behind enemy fighters suddenly matched or exceeded their performance. The difference was not only mechanical but strategic. High boost capability expanded mission profiles, increased interception success rates, and provided the tactical flexibility needed to defend British airspace. Ricardo's research had given Britain a weapon hidden inside the engine itself, one that altered the balance of air combat without requiring new airframes or new factories. By the middle of the war, Ricardo's contributions were woven so deeply into British engineering that they were often invisible to the public. His institute continued producing critical data for government agencies, engine manufacturers, and fuel suppliers. He guided additive selection to stabilize combustion under higher loads, advised on refinery processes to maximize octane output, and supported the shift toward fuel blends optimized for high-altitude performance. The more the war demanded from engines, the more Ricardo's scientific foundation proved essential. The combustion maps he created became reference documents across the aviation industry. His explanations of knock behavior were copied into manuals, training courses, and design guidelines. Engineers who had once relied on intuition now used quantitative data to push machines further than wartime stress had ever allowed. In a conflict defined by production, logistics, and technological escalation, Ricardo provided Britain with a stable scientific anchor. The RAF could scale engine manufacturing, fuel production, and aircraft deployment with confidence because the underlying science was sound. As the war entered its most intense years, one question guided the next phase of his work. How much further could British engines be pushed before the limits of combustion were reached and new forms of power were needed? What new challenges would Ricardo confront as the war moved toward its most demanding and technologically complex phase? As the Second World War reached its peak, engineering demands intensified beyond anything Britain had confronted before. Aircraft needed more power, longer range, and higher altitude capability. Bombers crossed continents. Fighters operated at the edge of their structural limits, and engines were pushed through cycles of stress that no pre-war designer had anticipated. Through this escalation, Ricardo remained a central figure. His institute provided the data that allowed manufacturers to refine engines under extreme conditions. Combustion stability had become a national priority, not just for fighters, but for every military machine powered by gasoline. Ricardo expanded his research program to test fuels at unprecedented pressures and temperatures, building new experimental setups capable of simulating the harshest possible environments. He explored how detonation behaved under rapid load changes, how additives influenced flame propagation at high altitude, and how chamber geometry affected power delivery during extended boosts. Each dataset filled gaps that could have crippled Britain's technological development. As engines grew more complex, Ricardo supplied the clarity needed to push them safely toward new performance thresholds. The Merlin engine, now the heart of British and Allied air power, continued evolving through the war. Later variants demanded even higher boost pressures and more stable combustion under heavy supercharging. Ricardo's research guided each major redesign. He advised on piston crown shaping to manage flame direction, refined combustion chamber profiles to prevent hotspots, and provided octane calculations to determine the precise fuel quality needed for safe operation at extreme output. The combination of Ricardo's combustion science and Rolls-Royce's mechanical engineering created a machine unlike anything used in the previous war. Advanced Merlin versions powered the Spitfire during its most demanding missions, the Mosquito during high-speed raids, and the Lancaster during extended bombing operations. The engine's reliability under immense load came from a scientific foundation Ricardo had built long before the conflict began. His influence reached beyond Britain. American manufacturers studied his work as they developed high-altitude engines for the Pacific and European theatres. His findings on detonation, mixture motion, and octane dependence shaped engine development across the Allied world. As Allied strategy expanded, new challenges emerged that required Ricardo's expertise. Long-range bombers faced severe performance losses at extreme altitudes, where cold temperatures and thin air disrupted mixture formation. Fighter escorts needed engines capable of sustained boost over long flights, something early power plants struggled to deliver without overheating. Naval aircraft endured violent shifts in load during carrier operations, exposing engines to stresses that caused failures in fleets lacking. Rigorous combustion research. Ricardo addressed each issue with the same precision that had defined his pre-war work. He explained how mixture strength must vary with altitude, how intercooling influenced detonation margins, and how fuel volatility affected cold weather performance. His reports guided modifications to carburation systems, ignition curves, and thermal management. These refinements prevented numerous operational failures, increased engine life, and ensured that aircraft deployed across continents could maintain consistent performance. Even while supporting wartime engineering, Ricardo looked ahead. He understood that internal combustion engines were reaching a level of complexity where guesswork was no longer viable. Nations needed scientific institutions capable of exploring combustion with rigour, precision, and long-term vision. Ricardo strengthened his institute, creating a post-war research framework that would influence everything from automotive engines to industrial power systems. His work contributed to the development of standardized octane ratings, provided the methods used to evaluate new fuels, and shaped the way engineers approached engine design across multiple industries. These contributions were not dramatic in a public sense, but their impact was enormous. Modern internal combustion science can trace much of its methodology to the systems he established during and after the war. When peace finally arrived, Ricardo's legacy was already secure. The aircraft that had defended Britain, supported Allied offensives, and shaped the strategic balance of the war were products of engineering guided by his principles. The machines that ran hotter, climbed faster, and survived longer did so because Ricardo had explained the laws governing combustion under extreme stress. His work bridged two eras of technological development. Before him, engines were built through intuition and trial. After him, they were designed through quantitative understanding. His influence extended across aviation, automotive engineering, fuel chemistry, and military research. Few engineers contributed so much to the survival of their nation while remaining almost invisible to the public. Ricardo did not view his achievements as wartime heroism. He described them as the natural outcome of scientific curiosity. Yet history tells a different story. When the war demanded engines capable of extraordinary performance, Britain possessed them because Ricardo had spent decades preparing the scientific foundation. His laboratory experiments became strategic assets. His combustion maps became national infrastructure. His insistence that engineering must rest on clear data rather than tradition reshaped the way nations designed machines of war. Internal combustion had unlocked the modern world, and Ricardo had unlocked internal combustion. He left behind a discipline that engineers still depend on, a legacy built not on slogans or symbols, but on accuracy, clarity, and the relentless pursuit of understanding. As the world moved into the jet age and beyond, a question remained for every engineer who studied his work. How many of the breakthroughs that defined modern power would have been impossible without the science Ricardo spent his life uncovering? What would the future of engineering look like if Ricardo's level of scientific rigour became the global standard rather than the exception?